Hello everyone and welcome. My name is Helena Blackbright and I'm here from Automation Region today. I'd like to very proudly welcome you to this IndTech Silicon Valley Quantum Talk that we have had the honor to co-arrange together with Romania. We have a very inspiring hour ahead of us where we will meet 7 highly distinguished experts in quantum computing, and they will help us to at least get a glimpse of what the future of quantum computing holds for us and how it has the potential to both revolutionize and disrupt various fields and industries. I also like to congratulate the audience here today because I think this will be a well-spent 1 hour. We're expecting more people to come, but we will slowly start. And before we welcome our guests, the people that we're really here to listen to today, I will let 2 colleagues in, Peter Wallin and Prachi Vakaharia, and they will tell us a little bit more about the initiatives behind today's talk. Can I start with you, Peter? Peter, would you like to tell us a little bit about the Swedish IndTech initiative?
Yes, sure. So thank you all for joining, and it's really nice to have this event together with Romanian and the Swedish Innovation Agency from Silicon Valley. And so thank you all, Frank Prachi and Marlou, and also Minna for putting this great event together. If we go back a bit, so in the title it says IndTech or IndTech Silicon Valley Quantum Talk. So I think we need to move a bit more into what IndTech is to understand this. And I guess during the 70s, 80s, and 90s, the industry went through a transition and installed a massive amount of automation IT system to increase the productivity and be more competitive. And these systems are to a large extent still in use, but they were not meant to be connected to the outside world. And now we see these new digitization technologies coming, like AI, machine learning, and also quantum computing, of course, cloud computing, and so forth. So I guess that when we talk about IndTech, it's how we can connect these new technologies with this traditional industry. So it's not just about how we technically do this, but also how we do it with these new business models might be needed. So how we connect it, what services are needed, and so on. And to connect to this Silicon Valley project, and so we, as you probably know, a lot of these emerging technologies stems from Silicon Valley. So since about a year, we've been running this project to bridge the gap between Swedish industry and the US, and in particular Silicon Valley, just to increase this cross-Atlantic collaboration and accelerate this digital transformation that is happening right now, so we can go towards, especially towards a more sustainable industry. So that's more about the product that we're running, and also a bit about the IndTech. So over to you, Elena.
Okay, thank you. Thank you very much. And what we do, I think is really interesting, really important. And today we are extra proud to say that we co-arranged today's talk together with Romania. And I'd like to welcome you, Prachi. Can you tell us a bit more about that initiative?
Absolutely. Excited to be here and excited to have Womanium partner with both your organizations for this event. Womanium, as the name suggests, women and the element of science. So that's why the name Womanium. And the goal of Womanium is to advance people, especially young women, in the cutting edge of sciences and make the scientific leaders of tomorrow. And this program we started in 2017 with the emphasis of science needs more bright minds, and we need more bright minds entering into the scientific domain and creating the technologies of tomorrow. So this is where one of our current programs is in quantum computing. And we're really excited to partner with you in closing these gaps between academia and the needs of industry, between the different countries, as well as we all look to create the quantum computing future of tomorrow.
Okay, thank you very much. And that is such an important work you do by several reasons, because as you say, when something is really new and we need to bridge those gaps, when we develop the new, we need to have representation in several ways. So thank you very much. You will come back in the panel later on. We will meet our first keynote, who will both help us getting a better understanding of what quantum computing really is, and will also provide us with some practical examples that I think many of us will need to get a grip of it and see the future. So together with us, we will have Dr. Sam Stanwick, is the Group Product Manager of Quantum Computing at Nvidia. Welcome. You hold a PhD in Applied Physics from Stanford University. And before Nvidia, I think you worked as technical lead at Rigetti Computing and also as a senior quantum engineer at Keysight Technologies. So in my position, I see you're well qualified in helping us. So please do that, and warmly welcome, Sam.
Thanks, Helena. Good morning, everyone. If you're in the US, good afternoon or evening if you're somewhere else. I just want to start by first thanking the organizers of this event, Vinnova, Womanium, and IndTech for the opportunity to speak here. I know there's going to be another great talk and a fantastic panel after this with a really great mix of people, and it's really an honor to get things started. Since I imagine there's a range of knowledge of quantum computing here today, I thought I'd start by just talking a little bit about, first what quantum computing is generally and the state of things today, then get into some potential applications and the reasons to be really excited about quantum, as well as the flip side of that, which are some of the challenges that need to be overcome to get to quantum computing being really useful and to realize these exciting applications. And then I'll finish up briefly by talking about the role Nvidia is playing in quantum computing. So I'm not going to try to completely describe quantum computing here, but I think one thing that's important to understand is it's a completely new computing model. So it's not, hyper accelerated computing. The physics at a fundamental level is different. The way quantum computers work is fundamentally different than classical computers, and the applications are going to be different. So there are going to be some things that quantum computers eventually do really well, and some things that they'll probably never be good at. And I think in the very long term, we're going to talk about some applications today, but we really don't know kind of what that whole set is going to be, and I imagine there'll be things that we're not even talking about today. So that's incredibly exciting. We do have some ideas for potential use cases already, and some really promising work getting started. One big area is in simulating quantum systems. So there's reason to think that the most natural way to study a quantum system is with a quantum system, and so quantum computers have the potential to have advantages in areas like simulating chemistry and simulating biology for applications like drug discovery. There's also a whole range of potential applications in optimization and machine learning for fields like finance, automotive industry, energy, and more. And I'll talk about that a little bit more later. And another really exciting trend is the progress in quantum systems. So on the right here, I'm showing scale of public quantum computing systems versus time over the last decade. And it's been really remarkable. So 10 years ago, we were talking about usually a couple of qubits at most. Today, there are many systems with tens of qubits, some with over 100, and progress seems to be accelerating, which is really, really nice to see. So in terms of applications of quantum computing, I kind of want to big picture group them into two areas. So there are a few algorithms where there are known proven algorithmic speedups. So two examples are Shor's algorithm, which is for factoring numbers. There's an algorithmic exponential speedup using a quantum computer for this. Applications obviously to cryptography. Another algorithm is Grover's, and this is for unstructured search. So this is a quadratic speedup, but has a much bigger range of potential applications. And in terms of when we can expect to get here, I'll get into this a little bit more later. But both of these are going to require qubit scale and performance far beyond what we have today. Likely thousands of perfect qubits to have an advantage over classical computers. And then in terms of other applications, there's kind of a whole range of exciting possibilities before we have thousands of perfect qubits. So it's important to understand that for these, quantum advantage is an open question. But what's what's exciting is there's a range of potential areas where quantum computers can be useful, especially in combination with classical computers, before we get to thousands of perfect qubits. So one of these areas is chemistry, material science, drug discovery. So there's an algorithm called the variational quantum eigensolver and variations on that algorithm that are useful for calculating ground state energy, potentially can offer an advantage long-term over classical algorithms. And then, in optimization, there are, again, hybrid algorithms using a quantum computer and a classical computer with, a huge range of potential applications. A lot of optimization problems in many different industries. And finally, machine learning. So this has been kind of the most recent trend. And there's machine learning is a huge space. A lot of kind of the problems naturally map well onto quantum computers, especially problems based on quantum data. And so again, wide range of potential applications here. So this is all incredibly exciting, but I want to emphasize that much more work is needed on the research side to understand exactly if and when we expect to see quantum advantage for these applications. And then I wanted to kind of briefly summarize, the flip side of all these exciting possibilities, which is, the challenges we actually have to tackle to realize useful quantum computing. So I think the most obvious ones are in terms of quantum hardware on the left here. Maybe the most obvious one is scale. For a significant quantum advantage, we likely need thousands of qubits or more. Probably more important and more limiting than scale even is noise. So because quantum computers are based on quantum physics, they're susceptible to noise in a way that classical computers are not. And because quantum computers are essentially analog computers, if you try to do a computation with a quantum computer, each little error in an operation compounds over the course of the calculation. So you really need to get noise very, very low, much lower than it is today, and then probably using a tool called quantum error correction. And then the third one is speed. So we've spent decades making classical computers faster and faster. Quantum computers are at the early stages of trying to make them fast. So there will be a time where a quantum computer is algorithmically faster than a classical computer, but in practice won't be useful to use because of practical overhead to using a quantum computer. So that those challenges are hard enough on their own, and the good news is there are thousands of people across academia, industry, national labs, and elsewhere working on them. And then there's another set of challenges, quantum software and algorithms on the right here. So one thing we also need is better algorithms. So for the potential near-term applications I talked about a couple slides ago, it's an open question if there's going to be quantum advantage or what's needed to achieve quantum advantage. So this is a huge topic of research right now, and continuing to improve algorithms for noisy quantum computers can be very, very fruitful potentially. And then even for fault-tolerant quantum computing, for applications like chemistry, the picture is not totally clear when and how quantum computers are going to be better. And especially for cases where we have a quadratic speedup, we need better algorithms to get over the overhead of using a quantum computer. And then another big area is integration with classical computing and classical supercomputing. So all useful quantum computing is likely to be hybrid. There are some things that quantum computers will never do well. And so if you zoom out to the application level, that you always want to run some parts of a task on a classical computer, and then call the quantum computer for the bottleneck that it does really well. So we at Nvidia believe that the first useful applications of quantum computers are going to come from very tightly coupled quantum computing resources with high performance classical computing resources. And so that's going to take lots of work in software and hardware to optimize that interface and make it something that's easy to program and use. And so Nvidia is kind of tackling both of the challenges on the right, both of the software challenges. So for better algorithms, a really important tool is quantum circuit simulation. So because quantum computers today are smaller and noisier than what we need to run useful applications. If you want to kind of understand the most important questions about new quantum algorithms, that's all done in simulation. So things like what algorithms are most promising for near-term or long-term quantum advantage, what the requirements are going to be in terms of number of qubits and error rates, and things like what quantum processor architectures are best suited to realize valuable applications are best done in simulation, because with a classical simulation of a quantum computer, you can achieve scale and performance far beyond what you can with a quantum computer today. And then the other big area, as I talked about in the last slide, is hybrid quantum classical computing. So how can we integrate and take advantage of the great tools that we already have today in classical HPC to accelerate hybrid workloads? And how can we make a quantum computer something that you don't have to be an expert in quantum computing to be able to program, but if you're say a quantum chemist, you can take your quantum chemistry code that you already have and start leveraging quantum computers to see if it can be accelerated. And then the other side of that is can we take advantage of classical acceleration for a lot of the problems that go into making a quantum application run well. So things like decoding for quantum error correction, or circuit synthesis to make sure you have the optimal quantum circuit. We see a lot of opportunity here. And then so in the last maybe five minutes of the talk, I'm just going to talk about what Nvidia is doing in these areas. So our product for quantum circuit simulation is called cuQuantum. And so it's a platform for accelerating quantum computing research. So if you have been working in quantum computing or are somewhat familiar, you've probably heard of frameworks like CIRC and Qiskit and PennyLane. So cuQuantum is not one of those, but it's a set of libraries that sits beneath them and accelerates them on GPUs. So if you're coding in CIRC or Qiskit or PennyLane or one of these other frameworks that we're integrated with, you can use cuQuantum on GPUs to get dramatically accelerated performance, simulate much bigger circuits without having to change any of your code. And so I'm not going to talk too much about cuQuantum, but just wanted to give one example of the kind of thing that you can do, simulating quantum circuits on a classical computer. So one problem that's particularly interesting for near-term quantum advantage is max cut. So max cut is a graph optimization problem with lots and lots of potential applications, including clustering. It's also potentially a very good fit for nearer term quantum advantage, and also a very good fit for classical simulation. So we used cuQuantum working with a team from Nvidia research, and we're able to simulate a max cut problem with up to 10,000 vertices, so using 5,000 qubits with 93% accuracy. So why is this cool? It's not better than the best classical algorithms still, but it's far beyond what can be done with a quantum computer or other simulators today, and allows you to really kind of test algorithms or tweaks to algorithms at scale and understand when quantum computers get to this level, what are the algorithms we're going to need to run, and will they have advantage versus the best classical algorithms. And of course, this generalizes to a broad range of algorithms and applications that we're starting to explore. And we're working with a huge number of groups across the ecosystem. These are some of the quantum computing companies and HPC centers. There are also academic groups and pharma companies not listed here, but really kind of seeking to enable the whole ecosystem and researchers everywhere with this. And then in the last couple minutes, I want to talk about a topic I find fascinating, which is how hybrid quantum algorithms are going to run, and how quantum computers are going to work paired together with classical supercomputers. So to start, as I said, all useful quantum computing is going to be hybrid. So you can think of a code that exists today on CPUs and GPUs, porting parts of it to a QPU to get accelerated performance on a bottleneck. So for that to be both kind of easy and useful, we need a kind of coherent programming model to enable someone who's a quantum chemist or with someone who's studying weather modeling or climate change to take the application they have and port parts of it to a quantum computer, or develop kind of natively hybrid applications that use and take advantage of the great tools from quantum computing and the great tools from supercomputing. So last month we announced the product for this. It's called CODA, and so the idea with CODA is to bring programming quantum computers up to the same level as programming CPUs and GPUs today. So create a single source C++ and Python programming model where you can within the same code make use of the best tools of classical computing. So CUDA, standard parallelism, OpenACC, OpenMP, together with both simulated and real quantum computers. So it's very important for work like this to be open. So CODA is going to be an open specification. We're going to open source the compiler and partnering with quantum companies across the entire ecosystem. So you may know that there are a range of kind of promising types of qubit technologies that have different strengths and weaknesses. Not clear yet what's going to be the best, or what's going to be the best for a particular application, or maybe all of them will end up being great. But we're working with a partner company from superconducting qubits, trapped ions, photonics, neutral atoms, and NV centers, and expect to expand this list dramatically. So the goal is that someone programming in CODA has a tool that's optimized for both classical computers and any different type of quantum computers, and can program them all together. So I want to leave time for a couple questions, so I'll wrap up now. I think the one sentence summary is there's incredible potential and exciting progress in quantum computing, but we're in early days, and there's plenty of work still to do. One big trend that we see is quantum computing and classical supercomputing becoming even more closely connected than they already are in the next decade. And Nvidia is committed to building tools and partnering with everyone across the ecosystem to help make quantum computing successful and help make it successful faster. So thank you so much for your time, and I'll take questions if there are any.
Lovely. Thank you so much. It's so interesting. And I who come from an innovation perspective, I think those phases of development are in a way the most interesting ones, because this is the phase where you actually design and form what will form our future very much, and what will disrupt what we know and how we do things. You talk quite a lot about the challenges that are ahead of us, that shows us how early in this process we are. But I have to ask you, I mean, what do you see? What type of impact do you see for the industry in a more shorter term? And what short term would that be? Is there any impact for everyday companies or the larger companies within, say, 5-10 years?
I think that's a that's $1 billion question. I think my perspective is within 5-10 years is very likely.
Yeah.
And I think things like using quantum computers for simulation of quantum systems are extremely promising. There's also some recent work in quantum machine learning that's extremely promising for nearer term quantum advantage than something like Shor's algorithm. So that's very exciting. I think I'd be very interested also to hear the panel's thoughts on that, because I'm sure there'll be a lot of different perspectives coming from you, depending on where you're coming from.
Absolutely, yes. And Yoto, I think one of very interesting thing also that you talk a lot about is this the comparison both about pairing and working together with supercomputers and quantum computers. What problems are more suited for one or the other, would you say? Not when you pair them, but actually when you have them separately, what are they suited for?
I mean, when you have them separately, I'd say quantum computers. There's kind of a known set of problems that they're likely to be good for. So I mentioned simulating quantum systems. I expect we'll see an advantage from quantum computers for that, and then something like Shor's or Grover's algorithm. I think it's just a matter of improving the quantum hardware to the point where it beats a supercomputer. But we certainly expect an advantage there. I will say, at least in the near term, classical supercomputers will be more broadly useful, just because the same things that make quantum computers extremely powerful, make their scope a little bit narrower, and so there are some things that they won't be good at. So that's why I said we kind of see them as very complementary technologies. And so quantum computer accelerating the things that a supercomputer struggles with.
Interesting. We got a couple of questions from the audience, and I think we have time to look at them. So first is a question from Justin, and I'm reading. It's been said that the useful quantum computers, whatever that means, he says, are 50 years away. Back in 2022. What has Nvidia decided now is the time to try to invest? Why has Nvidia decided that now is the time to invest? Has there been any breakthroughs that triggered this one, or is it just a matter of time?
Was the number 50 years away?
2022, so 2002.
Yeah. So I think from our perspective, it's an open question how far away quantum advantage is. So I mentioned some possibilities much sooner than that. I think the reason Nvidia has decided to invest, the main reason is there's just been an explosion of research interest, and people who realize that even though quantum computing is not incredibly valuable today, it's worth investing in heavily because the long-term potential is so exciting. And we have a lot of expertise in accelerated computing generally, and especially building software and hardware tools to bring different types of computing together and make a useful system that anyone can program. I mean, there's a bit of an analogy to early days of GPUs before they became essential for scientific computing. So we see lots of potential, lots of interest, and an opportunity for the things we do to be very useful.
Okay, cool. Thank you so much. We have another question from Manuel, and if we can see if we can get a quite short answer on this one. And it says that, so today's computers are based on digital electronics. However, I've recently heard about the comeback of analog computers. and its possibilities in accelerating AI. Maybe a bit outside the topic of today, but he's asking if you have any research ongoing on this new area of analog computers, very briefly, since it's a bit out of scope.
Yeah, I'll be very brief and say I'm not the person to ask, but it's incredibly interesting.
Indeed it is. So, okay, well, thank you so much for joining us, and thank you for spending your time. Time is the most valuable thing we have, and for sharing your knowledge. And I, like you, look forward to hear the panel's reflections on what you talked about. We will now meet our next keynote, and who will give us a better understanding of why quantum computing is so interesting in relation to certain types of complexity and complex problems. Very interesting. So Dr. Prineha Narang, she is the Howard Rice Chair Professor in Physical Science at UCLA, where she leads the Narang Lab. She also holds a position as an assistant professor at John A. Paulson School of Engineering at Harvard University, and is also a PhD in applied physics from Stanford University, was named the top innovator by MIT Tech Review, and is dear to the founder and CTO of Alira, a quantum network company. So you, just like our prior speakers, seem very qualified in helping us understand more. Warmly welcome, Prineha.
Thank you so much for having me here. I guess a minor correction. I'm a Caltech grad, not a Stanford grad.
Oh, I'm so sorry.
Very proud of that. The previous talk really set us up in terms of, what the application areas are for quantum computers and what we can realize when we get to quantum computing at scale. This set of questions that we heard over the past few minutes, I think they're driving at the question we all want to ask. When will we be able to address these important problems, right, that we can't do in classical supercomputers, the ones that we can't do with existing GPUs on quantum computers? I think that is the question the field needs to answer. And there are many pathways for us to get to scale. The pathway that I want to convince you of in the next few minutes is that networking devices, putting devices together in addition to optimizing individual devices, will get us to scale. And that's where this idea of quantum networking comes into play. I'm going to tell you about this work with my Alira hat on and not so much my faculty hat. However, if our questions veer into the latter, that is also fine. Okay, so you might have heard about networks, and typically people have heard about networks entirely in the context of secure communications. This is something that lots of folks have been talking about. Two things I want to point out. Quantum networks, like classical networks, are much more general than just communication. Two, when we're talking about general quantum networks, we are not talking about key distribution, okay? We're talking about using entanglement-based networks. These are ones that actually use entanglement as the backbone rather than individual keys being shared, okay? And the reason those two distinctions are important is the following. When we talk about distributed or clustered quantum computing, where we think about putting together smaller quantum devices over a network fabric, it will become important that we're using entanglement as the backbone, as the resource in that network, and not thinking about things like trusted nodes or keys, okay? So the first two applications here, quantum networks, secure communications, and distributed quantum sensing, I won't touch on. That's not the reason we're here today. I do want to talk about clustered and distributed quantum computing, right? So the idea is as simple as it gets, right? We can build a larger quantum computer by literally building a larger quantum computer, or we can build by connecting different QPUs together. So the previous talk introduced, the idea of noise and optimizing individual devices. And one of the reasons we can't get to the biggest, baddest device is because of this issue of noise and the challenges associated with decoherence, right? So when we think about connecting various quantum devices, well, we could get to scale that way. Sure, that's one approach. The question you'd want to answer is, how do I connect? For sake of simplicity, let's just think of two devices. How do I connect them together such that I'm actually creating a larger single device rather than just two devices that are connected over a classical network, right? So this is the simplest possible way of saying, if I connect two quantum devices over a classical network, I don't magically have a larger quantum device. However, if I can share entanglement across those devices, if I have a way of quantumly connecting them, I have a possibility of getting to a larger device. Now, it won't be as simple as A plus B. There is some resource overhead that's going to go into this. There's some number of qubits that will be involved in, say, the transduction, the conversion of information from, if you were doing matter-based computing, to optical, and then back to matter-based, right? So there's going to be a little bit of resource overhead, but it is a pathway to scale. The second reason you'd want to think about a networked set of quantum devices is that you could use heterogeneous quantum computers in one larger architecture, right? So we hear about the advantages of different qubit modalities all the time. We hear that there are certain systems that have very fast gates, certain others that have long coherence times, some that essentially are acting as a memory, except a quantum memory in this larger architecture. Now, you could put those together and think about a way of doing this heterogeneous quantum computing where you're using the best of each of those qubit modalities in a single system. And in order to do that, there are some challenges you'd want to overcome, right? You need some fabric. And I keep using the word fabric because that's a good visual. And I think visualizing entanglement for people can be quite daunting, but you can think about this fabric as essentially being the quantum version of Mellanox. This can be your, pick your favorite analogy for what this would look like. And you're essentially able to interconvert your qubit into this flying qubit, the photonic fabric that would end up essentially pulling these together. Now, does it have to be photonic? No, there are other phononic and other modalities. I'm not going to touch on those, far too technical for this situation, but I'll just say that for us to visualize, think of it this way. I have a superconducting system. I have, say, another trapped ion system, and I have some neutral atom system. If I can go from one to optical and back to one of the other qubit modalities, I have a way of connecting these with this fabric. Now, this is actually something that lends itself well to this idea of we'll have data centers, we'll have quantum data centers where people, different vendors, perhaps the one we just heard, some of the others would all come together. Their devices would be housed in a single location or sets of locations, and you could think about actually connecting these without really any losses because now they're co-located. And that problem in some ways is easier to solve than the problem of, say, a point-to-point or cross the country network, where you certainly will need other technologies that have yet to be developed. So the clustered and distributed quantum computing application is both a pathway to scale and something that is immediately or nearly immediately realizable. And I think that it will allow us to get to these, quantum software applications with materials, drug design, optimization, all kinds of things. So let me just spend, a few seconds on these applications again, because they were so well covered in the previous talk, and emphasize that, people who are working in materials design, people thinking about drug development, or thinking about even applications in machine learning, they have many options for types of compute architectures. And the question that we should be trying to address in quantum computing is not just, is there a threshold that we've hit that we wanted to in say, a quantum advantage, or, pick your favorite metric, but how does what we're predicting, how is what we're bringing in the form of compute capability surpassing existing technologies? And that's a very high bar. In fact, that's a higher bar, as it turns out, than just saying we've achieved practical quantum advantage. So with my faculty hat on, I'll say that, we do a lot of work in materials design. We've thought about materials and molecules that are strongly correlated. And as it happens, you can actually get very far with simulating these on large GPU architectures. We've done calculations on the Summit supercomputer and now more recently on the Frontier system. And it's not an apples to apples comparison when you say, how am I going to, surpass all of those simulations using quantum computers? And that's where people, have really started to say, let's come up with rigorous benchmarks. And I could, give a whole talk on benchmarks, but I'd say from the standpoint of people who have these problems, they want these problems to be solved better, faster, and cheaper, okay, than they are now. And they also want us to think about problems that you couldn't solve any other way. If you can't do it better, faster, cheaper, at least do something that other compute architectures cannot do. And I think this is where there is an opportunity in developing new algorithms. Of course, the variational quantum eigensolver, QAOA, and all of these have been around for a while. People have done amazing things with them. But I think if we stop there, we would really be limiting ourselves to then having to compete on that better, faster, cheaper vector, rather than looking for problems that are not solvable any other way. There are also problems in logistics, financial modeling. The list really does go on. And I think there are other vectors for optimization that are maybe not so relevant for drug development and material design. And all of these, and this is for students or junior researchers who are on this webinar, there's an opportunity to come from very, very different disciplines. There's an opportunity to come from computer science, software engineering, of course, but also from the hardware and from the standpoint of people really thinking about engineering each of these devices individually. Okay, so back to this idea of clustered and distributed computing, right? So as I said, you could get to more qubits, right? Or get more complex quantum architectures to exist first by scaling up, right? So you can think about more qubits on a single processor. And there'll be some capacity limits there. We might saturate at some point. Whether that number is thousands or 10,000s, there will be a point of saturation for how many qubits you can put on a single processor meaningfully, okay? The other approach is scale out. And I'd argue that we want to do both scale up and scale out, right? So you can cluster these different processors with each other and eventually get to a number that looks like millions, or pick your favorite very large number of qubit number. Challenges here are frequency conversion or transduction, right? We're talking about, so the only way we know how to send qubits around are over things like photons or phonons. So, but those don't tend to be the architecture that we're using for compute. You could think about an all photonic architecture. Let's set that aside for a second. Typically, what you're trying to do is go from superconducting to optical back to superconducting, or superconducting and trapped ion. And you still have that frequency conversion or transduction step to solve. So interconverting between qubit modalities. And there's a lot of work happening in thinking about such hybrid quantum systems, thinking about problems in transduction, and also thinking about algorithms that work for such architectures. Now, if I just took an algorithm that works through this architecture and ported it over here, that would not be efficient and certainly wouldn't do everything we expect. But if we can overcome some of these challenges, from a hardware standpoint, we would still have those software challenges. And I think there's a lot of work to be done there. So, over time, of course, you could think of very complicated networks that become available, right? So ones that involve repeaters, et cetera. And you could really think of an entire quantum internet scenario where you have quantum computers that are connected with each other. You have quantum sensors and also communication nodes all piggybacking together. This is not all that different from what we have in a classical system today, except that for everything here, you're using entanglement as your backbone. So with that, I was told I have about 10 minutes. So I'll conclude and say that, there's a lot of interesting, both technological and fundamental innovation to be done at the intersection of networking and quantum computing. This is an area where Aliro has engaged network engineers from very well-established classical network companies, as well as folks who are coming from a quantum, both physics and quantum computing background to really come together and get us to scale in this field.
Yeah,
So
I think, as you said in the beginning, one of the questions that people, I guess, want to know is when and how much, and when is it, when we're going to see the impact of it. And I think something that's very interesting is, as you say, when we start to look at the questions or the types of problems that we have not been able to solve before, that we need to solve them in a new way. So from your point of view, when would you say that we would start to see an impact? When can we actually, see an impact from this novel way of addressing problems that are complex?
yeah, so that's the question that we've all been asking. I'd say we will see, and we are already seeing, an impact on predictions being made for materials and molecules. Okay. That impact doesn't have to be quantum only, right? So that impact has come through hybrid classical quantum computing, leveraging the best of all possible architectures, right? And this brings me to the key point I'm really trying to make here, that impact isn't about how you did it, it's about whether you solved a problem. And if we're thinking about solving the problem here in the now term, we're going to need to actually use both quantum and classical resources. I think the scenario where we're using quantum-only resources is something that is on the horizon. However, we need to get to scale. And I think that's something that has a few engineering challenges ahead. And I sound like the typical physicist saying, oh, all it is engineering. And that's not what I'm trying to say. I think what I'm trying to really emphasize here is that some of those engineering challenges are being worked on with breakthroughs coming every day, right? You see phenomenal papers appearing from academia, from industry, from startups, but we haven't exactly solved the problem yet. And I see here in the chat people asking, well, there are roadmaps, there are all these things that have been released. I take those roadmaps with a giant grain of salt, because I think some of those roadmaps are aspirational. They are relying on this cadence of breakthroughs to remain the same. And it will to some degree, but I think to some degree, we also need to realize that, there are challenges. For example, in transduction, there's some challenges in frequency conversion that we haven't yet solved, and we haven't yet solved the level of efficiency we need them to be solved. So just because somebody has a single device that works in their lab doesn't mean that that's a device that you can go buy and duplicate in an industry setting.
Lovely. What do you wish for the coming years? What do you hope for?
Well, I really hope that this intersection, this interaction between people who are coming from networking, people who know how to connect these things together, and the folks who are working on quantum hardware, who maybe don't have that networking background, but have very, very good understanding of the types of qubits and how you can actually avoid decoherence and errors, can work together to get us to scale. I think that it's not an either or. I think it's a and kind of situation, and that's something that I hope the field can realize and work on in the near term.
Absolutely. And I think you're absolutely right. And as I said, when we're talking with Sam, I think in early phases of innovation, working together, cross-boundary, and actually seeking new ways to form things together with people who might not have worked together in other fields, I think that is essential, and that is an important path forward. So thank you very much. I look forward very much to hear the panel's reflections on both your talks. And thank you for your time. So I will be very short in your introduction, but I am so happy to have you here. And we have Prineha Vakaharia from Romania here that we met already. Welcome. We also have Dr. Marlou from the US National Institute of Standards and Technology and also Georgetown University. Happy to have you. Welcome. We have Dr. Philip Krantz from Keysight Technologies. Lovely to see you. Thank you. And we have Dr. Jeff Grover from the Engineering Quantum Systems Group at MIT. Lovely to have you here. Welcome. And we have Dr. Barbara Wellman from the Technology Consulting Unit at Deloitte. Welcome. Lovely to have you here. As a first question, general open to all of you, what is your reflections on the keynotes that we've heard? What do you say, Marlou? Do you have any spontaneous reflections?
Wonderful keynotes and highlighting exactly the areas of technology where quantum computing can contribute so much. Health, finance, indeed, drugs design, energy, optimization problems in traffic. There will be huge breakthroughs the upcoming years.
What do you look forward for the most? What are the things that you are eager to see?
Personally, from my professional background, I'm in materials research. But from a personal perspective, I really look forward to the drug discovery part. At the moment, drugs design takes several years. You calculate 100 or 500 molecules, you synthesize them, you measure them. It takes several years. It costs a lot of money. Using quantum computing, harnessing the principle of superposition, you can sample a few billions of molecules in a few months to see if they would be suitable drugs for certain diseases. And that will benefit mankind as a whole.
Oh, that's lovely, isn't it? What do the rest of you say? Do you have what is your reflections on what we've heard? Jeff, what do you say?
Yeah, I think it's definitely a very exciting time for the field. And it's interesting to see how it's changed since, I mean, I remember reading books about this when I was an undergrad in like 2008, and to see how quantum computing has changed since then, to have companies with actual roadmaps that they're ostensibly sticking to is something that was sort of out of the realm of my conception 15 years ago. And I still think, I guess as we heard in the second talk, like there still needs to be this kind of cadence of breakthroughs that happen all the time. And I think in our academic group, that's what we're trying to focus on, are these like rabbit hole types of areas that maybe companies won't have the bandwidth to kind of focus on. Of course, they're going to have internal R&D, but you know, they need to be very like have their eyes on those moonshots that they've put their stakes in the ground. And so I think it's interesting to play that smaller role of going down the rabbit holes that they might not have the time or bandwidth to do, and see what like the next generation components might be for the quantum computer of 10 or 15 years from now.
Okay, and you are brave enough to give us years here, 10 to 15 years. Thank you.
Oh, yeah, I guess that was more of a statement of, you know, there are roadmaps, I guess, for the next decade, you know, out to 2029 is maybe the longest term one I've seen. But there's probably going to need to be components, qubits with better coherence, transducers, like Professor Narang had mentioned. And these are the things that will probably take that extra, you know, 10 or 15 years to then be integrated into the production systems, I guess. But I am coming from an academic lab, so I probably have more pessimistic views than some of the industry.
But that is important as well, isn't it? So the rest of you, what do you say, Barbara? What do you say? What is your response on what we've heard?
Yeah, so I mean, part of my day-to-day job as a consultant is, of course, to run around in clients' companies and try to find use cases that might benefit from quantum in the future. So it's actually quite refreshing to me that I have a group of people who is so down to earth, I would say, in regards to when do we see a benefit and an impact. But that being said, I want to emphasize a bit that what we heard today so far is kind of a list of near-term applications, right? And I believe that when we're looking like moving from the near term to the long term, this list is really not ambitious enough. So I absolutely believe that in the long term, there are much more use cases that will have a very large impact from quantum. we just have to be a bit careful which timelines we predict, right? I mean, and so the argument here is not new. I'm sure you heard it all before. So when the classical computers were invented, no one imagined the internet, no one imagined Zoom calls and blockchain and metaverse and everything that we have nowadays. So it is really unlikely that people in 10, 15, 50, whatever number we heard now, once we are there with quantum computers, will stop at optimization algorithms, traveling salesperson problems, or even just ground state calculation in molecules. So the use cases that we will see, well, made first, or Prineha said it as well. So there are use cases that will be possible for the first time due to quantum. They are just beyond our current scope of imagination today. So there's much more to come. So let's not only look at the near term, let's look at the long term when it comes to quantum.
Yes, and I think that's very interesting. As I said, my own background is in innovation. And I think one of the most interesting parts about talking about technologies like this is the long-term perspective, that we know that we are forming something that will change maybe everything, but we don't know how and why. So let's come back to some of these questions. How about you, Philip? What is your take on what we've heard?
Yes, I think everyone agrees on that quantum computing is something that is long-term per definition. Yeah, just as Jeff mentioned, that I think there's always been this time frame of 10 years ahead. Since I started, it was 10 years, and it's 10 years now. so I think the field as a whole has become a little bit more aware that the expectation should be that we should not revolutionize everything tomorrow, but it's more about the mindset about quantum computing and about the thoughts behind how to design algorithms, for instance. So one thing that has happened a lot the past years now has been that industry has gotten more and more involved. And I believe that this will and has already started a chain reaction of adding more and more workforce into quantum. And I think that is by far the most important factor here, that there's just more people thinking about these problems. And I think that that's going to be key to success in many aspects here.
Yes, indeed, I do. So how about you, Prachi? What do you think?
Yeah, I'll add to Philip's point here about the need for the quantum workforce itself. I think this is a key and critical ingredient to nearly every technology boom we've seen. I'll just give you separate examples of electric vehicle technologies, or maybe even the automation field. So my day job, I work in the transportation field on emerging technologies, and we've seen booms of automation happening. I think similarly, booms and busts, where there's a lot of hype and then it fades down. And what's different about certain booms is that you have alignment of industry, you have alignment of the workforce, you have legislative alignment as well. So all these things come together, and then you really see an industry come together and actually deliver on the promises. And that's one of the role of Wominium, as well as with the quantum computing industry. How do we, again, make sure that we deliver on the promises that quantum computing has? And our little role in here is making sure that the workforce is ready to support and lead up to this delivering of the promises. And of course, when we do have working quantum computers, then build on those applications as well.
Yeah, cool. And you and Marlou, you really created one of the most impressive quantum computing education programs, and I guess this is part of the incentive behind that. I assume. Is there anything else that we done beyond that? Why is it so important beyond, as you say?
Yeah, absolutely. There was some seminal research done recently which looked at how do you create the quantum computing workforce of the future? And it found some very interesting things. First, it found that there are very different types of quantum-related jobs available right now, and the distribution of these job types is actually very, very broad. So this means that being specialized in quantum-only skills is actually beneficial only to a small amount of the workforce. That breadth of skills actually is very important. And then the second thing it found is that even though it seems that, again, quantum computing does seem intimidating. It seems like one needs to have a PhD in the field. Of course, there are a lot of positions open for PhD students, but the majority of roles still have no preference for someone with a bachelor's degree, master's degree, or a PhD. And what the industry consensus was that it's more about the skills that the student has and less so about the specific degree itself. So that led us to question, well, how do we create this workforce of the future? And we realized that it's about quantum awareness, which is most important, less so again about that master's or PhD degree. And this is where we created the Women in Quantum Computing program in partnership with Dr. Marlou at NIST, to train young students in engineering domains, computer science, physics, in the cutting edge of technologies in quantum computing. And some of them are coming at the high school level, and others are, of course, coming at the PhD and postdoctoral level. But all of them today are able to contribute to the quantum field. So that is most exciting for us.
Yeah, and I think it's, as I said, I think this is really interesting because, again, you're talking about awareness, and I think that's very important because the people who are in the field, they drive it, they are very aware. They might be not aware of the other fields, other areas to consider, but if we let the development go along before we involve or engaged in it, it might be much harder to actually form what we want it to be. And for Jeff, I wonder how does the academia work together with business today? Is there a tight coupling? Because I guess we need that very much as well, as Pachi is saying.
Yeah, I guess so. From the perspective of workforce development, there definitely is. So I guess within MIT specifically, there's a couple of different ways we do that. So kind of at the younger level, there's this excellent qubit by qubit program that has been started outside of MIT, but actually a lot of students in our group have had a lot of involvement with tutoring and running sessions and actually teaching classes, which I think is excellent. And so that's the kind of thing that gets people interested in, I think, quantum specifically, but also just STEM more broadly at a young level, which is definitely going to be important for broadening the base of folks that we will then interact with at like a PhD program or somewhere down the line. We also have, like, through our Center of Quantum Engineering, there's this thing we call the Keysight, the Quantum Science and Engineering Consortium, which we actually partner with industry partners to work on a problem of interest. And so I think this kind of works two ways, where the students get some kind of eye into industry, the types of problems they're interested in, but then they conversely, the industry partners get to learn a little bit about quantum because they have deep technical expertise in something related to their industry, but not necessarily quantum. And so it's kind of like this two-way street of education where PhD students get exposure to some area of application that they might not have otherwise. And then the company also gets exposure to quantum. So, I mean, it's a small thing. We're only one place, but I think these kinds of things are now they exist more in the world. Like, I know there's similar programs at Stanford and other universities. So this is becoming the norm, I think, which is nice.
Yes, I think it's true. And I think another thing that is so interesting again is not Prineha, and I think you as well, Barbara, mentioned is that about not knowing what it's going to be. It's not only, and I guess that also students and companies work with that, but we are actually knowing that we will address other problems, we will solve them different ways. We're not really sure what will come. What do you say, Barbara, about, because that is not only fascinating and fun, there's always a slight chance of that there are risks that we cannot identify yet. What do you say about the risk part? Because I know you've been working with things like that.
Yeah, absolutely. So, I mean, that goes back to education, actually. I mean, obviously, quantum is an enabling technology, so people will be able to do very good things with it, things that are good for the environment, for society, for whatever, but they will also, well, if we follow the thought of what is now been done with classical computers, they will also do really stupid stuff and stuff nobody needs, but also dangerous stuff. so we don't know. So how can we prepare for this? So one thing is we have to know that quantum is coming and what will be possible. And we have to think about ethics and what do we want to allow and how do we want to, well, as countries, but also globally, how do we want to deal with this? And this is a question. We don't know what is coming, and there's huge risks. So if you can develop individual drugs and medication, then of course you can also develop biological weapons. And then what do you do with these weapons? So some would say in some cases maybe it's justified to use these weapons if they are really targeted. But which cases are there? So this is a huge topic, of course, and well, way too long
Yes,
to
indeed.
come to a conclusion in 15 minutes. But yes, immense risk. Let's educate society. Let's educate the public. Everybody should know about quantum, not only the workforce, everyday people, so that we as society can have these discussions and come up with rules and with ethical standards and so on together. Yeah.
Yeah. I totally agree, and I think that is important. And it is important to do that early. I think before the problems has occurred, try to at least form a bit of a framework of what we think is good or not. And I was thinking when we're talking about these things, Marlou, you work for the National Institute of Standards and Technology. So this is a non-regulatory agency of the United States Department of Commerce, and it's has a mission to promote American innovation and industrial competitiveness. Why is NIST interested in quantum computing, and how does it drive innovation from a governmental perspective?
NIST is focused on the research that benefits US industry and society, and that means it's interested in quantum as a whole. This ranges from quantum computing to quantum sensing, quantum communication, various materials, quantum standards. It is in the name, NIST. Quantum effects are used for atomic clocks, defining better time standards, a better second for GPS and other applications.
Also, second, did you say that?
Yeah, a better definition of the
I
second.
want that.
Yes. On the other hand, also resistors, we need good standards for those. Then quantum computing will have huge impact, and NIST has been involved from the start, even when it was not known that it would be used for quantum computing. For example, already in the 70s, techniques were developed here to trap ions or to trap neutral atoms that are now being used as the basis for quantum computers. And that was not known at the time, that it would lead to those developments. Meanwhile, several Nobel Prizes have been awarded. So a lot of focus is on developing science and technology for quantum computers. But adding to the point that Barbara mentioned, quantum computers can make, but also break things. This especially holds for encryption. It can make encryption, but also break it, which can be a huge threat for society. And this anticipation that Barbara also mentioned is extremely important. We don't know when quantum computers will be that good, right? And NIST has done a survey among experts. We think, okay, around 2035, this can be the moment that we really have that quantum advantage and that quantum computers can start breaking encryption. And we all need to prepare for that. So there is a strong focus on post-quantum cryptography to develop algorithms that are robust against quantum. So we can have good encryption, and we need to focus on that now, 15 years ahead, to be protected in 2035 and beyond.
Is 15 years ahead, is that time enough?
We will see. Industry is more optimistic, so
okay, I'm happy to hear that. That's important. Yeah, but I think this is really important. I think this is a very similar discussion that you always have when there is a very disruptive new technology. There's always this discussion, and sometimes I've got a feeling that people who are not in it and who does not see any applications that affects them directly here and now, they have a tendency to discuss things like this as hype or not seeing the reason to be in it. But what you're saying is that we all need to be in the discussion. We need to know a bit more. So really interesting. What do we need to know? What is the baseline? What do you say, Philip? What do we need to know, everybody? How much?
And that's also a good question, and I believe that everyone, yes, from an interest point of view, I think quantum is it's obviously it's a very different way to compute things, but I do think that the answer to that depends a little bit on who you talk to. So what we have seen in my experience, what people like to know is how they get impacted by a technology. And when it comes to quantum, that's a little bit hard to predict how that will impact each and every one of us. But when it comes to commercial interest or companies that are interested in quantum, a lot of people want to be quantum aware, so that they want to be quantum ready when the technology hits the technology that they care about. And many times it could be that they are interested if something is possible to do at all, because that can have a disruptive effect on their main product, for instance, or the main interest of the company. So many companies invest a lot of time into learning what can be done in quantum and potentially how big quantum processor would you need to be able to do something useful for the problems that they have at hand. So I think that's a trend that we have seen in the past years, there has been many startup companies now consulting a little bit with larger companies to try to teach them and educate them and to discuss with them what do they need to know about quantum. And in return, the consultant company would need to know something about what this company cares about. So this is, I think, a dialogue that no one carries all the answers, but you need to talk to experts in different fields to find out where it has the most impact.
Yes, and I think this is something that cuts through everything I hear today. It's about we're early. It's about foresight very much. It's about scenario discussing actually and trying to be exploring the potential parts, even though we can't really say what they are, but really trying it out and involving much enough people from different fields so don't cut anything out, and that we are actually prepared and we have a preparedness because it might be very disruptive to us. You felt you spent years actually on developing the Wallenberg Center of Quantum Technology at Chalmers University here in Sweden. And they have a very strong focus on health applications. What are your thoughts on the applications in life science about when we're talking about awareness and trying to see what potential impact there is?
Yeah, that's an interesting question. So but before my appointment at Keysight, I worked as the scientific coordinator of this Wallenberg Center for Quantum Technology. And one core focus of the center is really to educate, if you wish, the Swedish industry about what a quantum computer can do, and for Swedish industry to educate quantum scientists of what these problems look like and what they do today to solve these problems. And talking about life science, there's a few different projects I know going on between this center and partners within life science. One of them is a company called SpectraCure in Lund. So that they try to, or they actually got quite far on this, to remove tumors, cancer tumors in the body using quantum sensing, the technique. So that's not quantum computing, but it's quantum technology. If we take an example from quantum computing, there's a lot of exploratory work here on how to design quantum algorithms for life science. And one example is a PhD student, Hanna Lin at Chalmers, who's collaborating with a PhD student at Sahlgrenska University Hospital. And what they are looking at is peptide packing. So one class of problems within protein scaffolding that I saw Sam mentioned also on one of his slides. And that work is mainly to look at how the quantum algorithm would be able to, if it would be able to speed up the simulation of this peptide packing problem. So it's more on the algorithmic side at this point and exploratory.
And you, Jeff, is what you do with your students, it's not also very much exploratory at this point, or is it about learning the technologies that is?
It's a mix of both. So I think some of the things we focus on are related to materials, like at NIST. So figuring out, you know, how do we make qubits smaller but maintain their good properties? How do we just, even if they stay the same size, how do we make them better? And some of those answers are going to be, and some of those questions will be answered by materials research. So that's kind of at the very fundamental level. 1 or 2 qubits, we're definitely not making a cloud quantum processor out of these things. But then we do have systems that are kind of in the intermediate scale between kind of that fundamental academic research and say what's happening at a Google or an IBM, where we have, you know, a system of 16 to 25 qubits, and there it's really about studying interesting physics problems that would maybe be difficult, not impossible yet, but difficult to do with classical computers, and kind of pushing the limits of control and calibration to figure out what we can do with them. And so I think one of the challenges for academic groups is to try to find interesting niches that industry is not necessarily interested in, because in terms of resources, we can't compete toe-to-toe with a Google or IBM. And so, you know, you have to get a little bit more creative about what you work on, so that you find those interesting things that eventually industry might be interested in. They can take those ideas and run with them. So that's very cool. But it allows the students to, you know, really exercise their creativity to find those interesting spaces to work on.
What are the most interesting spaces to work on at the moment, do you say?
Yeah, there's a lot of, I mean, what we call in the field, these like many body physics simulations, I think are very hot, and like simulating condensed matter systems. So whether or not they have actual application from a science perspective, you know, I think people are really interested in answering questions that were kind of posed by theoreticians and condensed matter 30, 40 years ago. And now we have these systems that can start to actually emulate those physics. And so I think that has become like a burgeoning field, both in superconducting qubits and neutral atom processors and trapped ions. Like every modality can target these areas. So from kind of like just a pure science and research standpoint, that's one of the exciting areas, I think.
Yeah. What do you say, Prachi? What is the most interesting field to focus on for the moment for you? What would you say?
Yeah, absolutely. For my domain, one of the strongest, again, my day job, I work in the transportation sector, especially on emerging technologies in transportation sector, transport as well as energy. And what's most interesting in this domain is battery applications using quantum computing technologies. So how do we make better materials, battery materials, and especially today when we're all trying to offset our carbon emissions, there's a huge push by the car making industry as well to move towards battery technologies. Hydrogen fuel cell is another application the industry is looking at. The question is, how do we make batteries with better range that are lighter? And of course, quantum computing has some answers here. Companies like Hyundai Motors have partnered with IonQ to help them investigate this. And I know other automakers are looking into different applications of quantum industry. So that's what excites me most.
And why is quantum computing so suitable for these problems? Is it because of the scale or the complexity, or
Yeah, it's the ability to test different scenarios and optimize for things, and it can let us do that faster, better, quicker.
Cool. So this is actually a field that you expect will have a potential very positive impact on our environment and help us solve some of the big questions.
Absolutely, even for renewable energy and a stronger renewable energy penetration. the battery capacity. Today we use lithium-ion batteries. They are fantastic, but of course can be improved. And then the question is, how do we come up with better battery chemistries? This is for energy storage. So again, we can have renewable energy, which, the sun only shines a number of hours of the day. The rest of the time, we do have to store that energy. And the question is, where do we store them? We need really robust batteries for this. And this is where I think for the advancement of different energy generation technologies, as well as, again, as I mentioned, with the automotive industry as well, of moving people and goods around, battery technologies have a lot of potential, and good batteries have a lot of potential. And this is where I'm excited to see how quantum computing can contribute to this industry.
Yes, indeed. I think we're all. How about you, Barbara? You're closer to the industry than, the researchers, as you said, and things like that. What are the hot topics in your mind? What are the most interesting parts to keep an eye on for the future? Barbara, did you hear me? Yeah.
Sorry,
okay.
I didn't realize you were
I'm sorry. It's probably me. I've had a rough afternoon, I promise you. So it's probably me. I was thinking you work much closer to the industry, and in a company like you do than the researchers, and need to, as you said again, the focus is a bit more here and now. What are the most interesting things to focus on for you in your area?
Yeah. So what we are working on right now mostly is optimization. It's not the most interesting in my personal, well, for me personally, but nevertheless, it's the one that is most suitable right now in the NIST era, because it's kind of like errors don't matter that much. Let's put it that way. So usually, what we do when we look at optimization at a client's problem, there is already a classical solution, and you can use that solution as a benchmark. And now bringing in quantum, you can only win. So either you get a solution that is better than the classical one, then everybody is happy. But if you don't come up with a solution that is better than the classical one, you can still use the classical one. But you learn something about quantum on the way, and then you can learn about the different views or how, like, the probabilistic approach of quantum versus the classical approaches. So a bit of a funny story here is as well. So we did this. So we had a benchmarked classical solution for an optimization problem that came in, did our quantum approach, and it was actually better. So not much, like 0 point something %. So really no quantum advantage here at all. Nevertheless, it was a tiny bit better. So that got the classical people then to say, well, no, this is no, this quantum can't be better than our approach. If we spend a bit more time in, tweaking our variables or whatever, we will come up with an even better solution. And they did. So, and that was perfectly fine, because so the management was happy, because in the end, they had a better solution than they started with. That solution wasn't quantum, didn't matter to them. But they know now when to, come in with quantum again. So we set some milestones that in X years, or when X qubits are reached, then try our quantum solution again, and then, have the same competition between the classical and the quantum again, and maybe you will, gain even more.
I love this. We should pit countries and academic universities against each other as well. Competition brings out the best amongst us. So why not?
This has actually happened kind of organically after the Google Quantum Advantage result in 2019. It has spurred a lot of classical high performance computing teams to really push the envelope, and especially from China. I feel like every month there's a new paper. They've come up with some clever way to do some tensor network simulation of quantum systems. So that is that's a great tangential benefit of this whole thing, is that it does spur classical computing methods, maybe unintentionally. They poke the bear a little bit, and this is the fallout.
Isn't that lovely? And especially since we know we have such a long way to go, if we can break this up in small chunks, we will have a really long sprint run. So with not so many minutes to go, what would you last like to pass on to the audience? What to think about, what to do, what you want to give them? Let's start with you, Barbara. What do you like to give them?
Well, I would say be a bit more ambitious. I guess, than the general tone of this. But no, as I said, I find it really refreshing because usually I talk to people who are, say, more on the overselling side than on the cautious side. But probably the best way is, as always, in the middle. So from everything you heard today, step it a bit up, but still be.
Okay, I love that. So
cautious.
step it up. Thank you. What about you, Marlou? What do you like to tell people to take away from today?
I would like to say quantum is the future and quantum is happening right now. Quantum optimization problems are already solved using quantum annealers, but especially it's the time to educate yourself. For young people, learn what quantum is about. Get that quantum literacy, get that quantum curiosity, and learn more. For people who are already in physics, electrical engineering, quantum field, build that bridge towards quantum computing. That bridge is not far away. You have great career opportunities with your background already, and just add that little bit of quantum computing to open that world for you. And it is only the start of a quantum computing journey. So join it from that start, and let's make that whole journey together.
Okay, lovely. So what do you say, Philip?
I would also like to build on what Marlou said, that I think what we need right now is just more minds and more backgrounds and more diversity in the field. So I think everyone comes in with different perspectives and different backgrounds, and I would not be afraid that quantum mechanics, it sounds hard, because quantum computing is not only about fundamental physics. It's about a collaboration between various kind of engineers, chemists, and that there's so many different backgrounds that blend together. So don't be afraid to enter this in one place where you feel most comfortable to start.
Lovely, thank you. And shortly from Prachi, what is your take? And
Wonderful. If you are a student looking to enter the quantum field, let us talk. We have the Women in Quantum Computing program. We had over 100 speakers come and present. Dr. Bill Phillips, Nobel Prize winner, who discovered, as Marlou said, how to laser cool and trap atoms. He came and spoke as well. We have a great collection of, Barbara, Philip, and in fact, Jeff and his lab at MIT, all coming and training you to the best of their knowledge. So come, let's talk. The second is, if you are a CEO or a startup founder looking to make an impact in the quantum field and start your own company, let's talk again. Our goal is to go from idea to IPO. It's to not only train students, but also have them build their own quantum startups and make their mark in the quantum industry. So again, if you are looking to start your company, let us talk. And lastly, if you're an investor in the field, what I've observed is learning from friends and colleagues at places like InQtel and other venture funds, that there's a dearth of investors in these fields. Again, a little bit of quantum computing understanding will help you understand which companies to invest in, which technologies to bet on, and how to go about managing your portfolio and your risks. So again, if you're an investor in the field, let us talk.
Okay, lovely. Thank you. And last out is you, Jeff. Very shortly, what you like to give the people when they leave here? What to think about?
I was going to say mostly what the last three folks had said about creating a more diverse and diverse workforce over many different axes. And so then I guess like the call to us in the field is to make a big tent to make sure that, we welcome more people into the field and that they stay here. So that's definitely a big charge for all of us to work on as we grow.
Lovely. So with that, we have to wrap up. We're a minute over time, but thank you so much for joining us, and thank you for sharing your thoughts. I sure hope that we will have the reason to talk again.